In this video, we're going to be learning about chiral molecules. That way we can identify chiral carbons in a molecule and identify molecules as either being enantiomers or diastereomers. Earlier, we introduced isomers, which are compounds that have the same chemical formula but are different substances. Isomers can either be constitutional isomers, meaning they have a different connectivity of atoms. Subtypes of constitutional isomers include skeletal isomers, positional isomers, and functional group isomers. And on the other side of the tree, we have our stereoisomers, which are spatial isomers. They have the same connectivity of atoms, but they have a different 3D arrangement in space. We had previously introduced our cis-trans isomers, which are a type of diastereomer, when we talked about our alkenes. So as a brief review, we talked about our different types of constitutional isomers before. Constitutional isomers. So constitutional isomers can either be skeletal isomers, meaning the molecules have a different arrangement of carbon atoms, as shown here with 2-methylpentane and 3-methylpentane. The carbon arrangement is different. We also have positional isomers, which have functional groups at different locations. So that's 3-pentanol versus 2-pentanol. They're both alcohols, but the alcohol is at different positions within the molecule. And then we have functional group isomers, which have different functional groups altogether, like that's an alcohol versus an ether, but they do still have the same molecular formula. Stereoisomers have the same connectivity of the atoms, but a different three-dimensional shape. For instance, your left hand is a mirror image of your right hand. So if you try to align your hands with them both palm up, then you won't be able to superimpose them on top of one another. So that means like they don't line up when you put them on top of one another. All of these chiral molecules have stereocenters, and stereocenters are also known as chiral centers. We'll be using the term chiral center more often. So we'll be trying to identify chiral centers in our molecules. Chiral centers are carbons that are bonded to 4 different groups. That's very important, 4 different groups. And so let's first practice trying to identify which molecules are chiral and which ones are not. So we're looking for objects that are not superimposable with their mirror image. Achiral means that it is superimposable with its mirror image. Achiral is another way of saying not chiral. So for instance, this sock here, I can do a mirror image and get another sock, but those 2 socks line up right on top of each other. That's different than like toe socks, for instance, that might have a bigger toe on one side for your big toe. But there's no like left and right socks. These are just regular socks, and you can put the left sock on the right foot or the right sock on the left foot. It doesn't matter because the socks themselves are not chiral. So the 2 socks are superimposable on their mirror image. It means it's not chiral. So let's try to identify these molecules as chiral or achiral. Go ahead and pause the video and try to think about this. Unpause the video when you're ready to check your answers. Okay, so our nails are achiral. When you pick up a nail, you can rotate it about this axis and it would line up with this mirror image. So that's achiral. Screws, on the other hand, are chiral. And that has to do with the threading here. the threads go around in a particular direction. And so, like, for instance, to tighten the screw, you got to turn clockwise, and then to untighten it, you turn counterclockwise. And so the mirror image of the screw would be the opposite, because it would spin around the other direction. I'll try to draw it here. So the threads on this make it a chiral object. This mitten is supposed to be one of those mittens that like has a really defined thumb area. Here, I tried to make it look a little bit more 3D. And so this I have as a chiral object because you would have like a left hand glove versus a right hand glove. This is a left hand gloved. This pencil is achiral because if you spin it around, it would look just like its mirror image. When we're looking for our chirality in molecules, we are looking for carbon atoms that are bonded to 4 different objects. Here we have a carbon that has the chemical formula Ch15V06. So that means it has 2 hydrogens on it. I'm going to color this hydrogen blue, just for reference. When I do a mirror image of that, it's here. Now you can see the green is on the right. So if I take this molecule and spin it around to put the green on the right, then I can align all of these atoms again. So I can do it. I can align them. So this one is superimposable on its mirror image. That means it's achiral. On the other hand, this molecule has 3 different halogens and a hydrogen. And so if I take the mirror image of that, you can see its reflection in this molecule. And now if I try to spin this molecule around so that the yellow is aligned over here, then the green and the red are not going to align with one another. And so this one is not superimposable on the mirror image. And so this means that these 2 molecules are chiral. This is one enantiomer of this molecule, and that's another enantiomer of that molecule. So here we have some pictures to help you identify what makes it a chiral center. We are looking for carbon atoms that have 4 different groups on them. So for instance, this carbon here has 3 hydrogens and this 4th group. So all of this is, you have to think like everything past the bond. So here we have 1, 2, 3, 4 groups, but 3 of these groups are hydrogens. So that's not chiral. Now if we look at the center carbon, we have this group this group, and this group. Now you'll see that I circled 2 methyl groups. Two methyl groups. And so that one is a chiral as well. Now this carbon is the same as this over here. This and that are just mirror image of each other. So this one's not chiral for the same reason that that carbon was not chiral. We have to have 4 different groups bonded to it. And so none of these carbons are chiral. If we look up at this amino acid, we have 1 group, 2 group, 3 group, 4 groups. And so this one has 4 different groups. And so this carbon right here in the center is chiral. That means if I take this amino acid and I take the mirror image of it, I'm going to end up with a different molecule. As we add multiple chiral centers into our molecules, we're going to have lots of different possibilities. Enantiomers are stereoisomers that are mirror images but not superimposable on one another. So if we put a mirror here, then this is the mirror image of that, but they are not superimposable on one another. This carbon is chiral because we have 1 group, 2 group, 3 group, 4 groups. So this carbon right here has 4 different groups on it. Likewise, if I look at this carbon, I have 1, 2, 3, 4 different groups. Notice how I circled that whole rest of the molecule? So this molecule has 2 chiral centers. That means there's a lot of different possibilities for the 3D arrangement of these atoms. And so when I take the mirror image of it, these will not align. Diastereomers are stereoisomers that are not superimposable, but they're also not mirror images with one another. So if we look at this wedge dash model of this molecule, you can see that this is sticking up out of the plane of the paper. This is sticking up. And so if I did the mirror image of this, then they would both be sticking up. But if we look at this molecule, this one is up and this one is down. And so there's no way I can take the mirror image of this molecule and end up with that. So these are not mirror images. But they still have some chiral centers in them. So we see here this chlorine has everything on this side of the molecule, everything over here, this chlorine, and then 1 implicit hydrogen. So we still have some chiral centers, but they are not superimposable with one another. But they're also not mirror images. So diastereomers, not mirror images, enantiomers, mirror images. Let's practice identifying the chiral centers in these molecules. Go ahead and draw these molecules on your note paper and identify where the chiral centers are. There might be multiple or none at all. Go ahead and pause the video and then unpause the video when you're ready to check your work. Okay, so when we're looking at this, we need to look at, we can immediately eliminate any carbons that have double bonds or things like that. And so this one is definitely not a chiral center because it has a double bond, which will not allow it to have 4 different groups. We can also immediately eliminate anything with 2 hydrogens on it, because if it has 2 hydrogens on it, then it's definitely not chiral. I switch color inks, and so now we can look at the remaining carbons. For this carbon here, we have 1, 2, 3, 4. And so this carbon does have 4 different groups. So I'm going to go ahead and put a star there. And then erase my red marks. Now we'll switch over to this carbon. This carbon has 1, 2, 3, 4. So this carbon also has 4 different groups, because that was not the same as that, which is not the same as that, which is not the same as the OH. And this molecule, this carbon here, has 1 group, 2 groups, 3, and then 4. And so this one also has 4 different groups on it. If I look at this, I have to remember that there are implicit H's at each of these vertices, so that each carbon has 4 different groups. That means that each of this point, all of these points are going to have 2 H's. And so that is not chiral. And same with this group at the end, that has 3 H's. So that's not chiral either. So the only thing left to look at is where we see 3 lines intersecting. And so we can see that we have 1, 2, 3, 4. And really, like, how you differentiate those are kind of irrelevant, because this is symmetrical. And so this group and that group are the same. And so this is not chiral either, because that group and this group are identical. Okay, let me switch back to blue, and we'll work on the next one. And this molecule, so this one had 0 chiral centers, this one had 3 chiral centers, to officially answer the question of how many chiral centers there were. This molecule looks a lot like this molecule, only now it has some differences. Now we have this double bond here. That's going to mean that each of these only has 1 hydrogen on it. But it also has a double bond between those 2 carbons, meaning these 2 carbons do not have 4 different groups, because they do have a double bond to them. So these 2 are still not chiral. And then same reasoning as before, each of those still had 2 hydrogens on them. This one had 3. So all of those carbons are not chiral. Now if we switch back to look at the one that we haven't eliminated, we can see that, so if we're looking at this one, now we have this group versus this group. And then of course it has the H and whatever, that methyl group up above. And so now if we look at it, this group and that group are not identical anymore. This one has a double bond and this one does not. That's different than that. So this carbon now has 1, 2, 3, 4 different groups on it. That means that this carbon is chiral. I'll go ahead and put a little star on it. So that one is chiral. That means this molecule has one chiral center. This one, we can eliminate the terminal ones because each of those has 3 hydrogens. That has 3 H's. Right, but let me write that better. That has 3 H's. Now let's look at the remaining carbons. This carbon here has 1, 2, 3, and then a 4th hydrogen. So that one is chiral. It has 4 different groups on it. This one is also chiral. Remember, it does have an implicit H. And so that's 1, 2, 3, 4. And so this one has 2 chiral centers because it has, let me clean it up, it's all messy. That carbon right there and that carbon right there. So all of the chiral carbons are identified in red, and all the not chiral carbons are in blue. Many of the drugs that exist have some chiral centers to them, and drug manufacturers have to be very careful about which enantiomer is released to the public or which enantiomer is used. And because your body does have very selective receptors, so it would accept one enantiomer of this molecule but not the other. So one drug might be actually beneficial and working, and another enantiomer of that same drug would be toxic. So we have to be careful to pay attention to which enantiomer we're using and all that good stuff, because your body will respond to these different enantiomers in different ways. Another example that's a kind of classic for this is recognizing the different smells between spearmint leaves and caraway seeds. Both of these have a caravone molecule in them, but this is an enantiomer of this one because of this chiral center down here. You can see that that's going from behind the plane of the board, behind the plane of the board. These are not mirror images of one another. So these are a pair of enantiomers. They are mirror images, but they are not superimposable on one another. They can form a complete sentence. So since they are enantiomers of one another, they do not have the same response in your body. Here's an example of naproxen, which is in a leaf. And you can see its mirror image here is not superimposable with itself, but that is its mirror image. This enantiomer is a liver toxin, so we have to make sure not to ingest that and only ingest that.